For chapter 25, since I didn't have time to go over those in class. Or maybe if I do this another year, maybe I did, but I still want to post them online for people who were absent. At any rate, this first example is one that is based on a book problem, but I modified it somewhat. So it says a 10 centimeter long wire, and that's that way, is pulled along a U-shaped conducting rail, like that, in a perpendicular magnetic field. So the field in this case I've just drawn into the board. I made the picture, they didn't have a picture with this problem. The wire has a resistance of 0.2 ohms and the rails have negligible resistance. So if it's pulled with a force of 1.0 newtons, what's the speed? Assume 4 watts is dissipated in the circuit. And then the second question is, what's the strength of the magnetic field? Well, it seems like, holy crap, what's the force in watts dealing with something like this? So the big idea is we would have balanced forces here. I should have probably said it was going at constant speed, but in this case it would be an instantaneous force and speed, I guess. So the pole is going to be to the right. The magnetic force for my diagram is going to be to the left. So I was told that the pole was 1 newton. And the force to the left is going to be the magnetic force on this wire. That would be equal to the magnetic field strength times the current times the length of the wire. Okay. Well, the only thing I know right now is 0.1 meters. I don't know either of these two. So I'm going to go back to this question, which is the strength of the magnetic field. So we were told that we had 4 watts when we were pulling with a force of 1 newton. Well, watts are a unit of power. That's equal to V times I, or I squared times R. Well, we were told that the circuit here, or this wire, had a resistance of 0.2 ohms. So I can use P equals I squared R, and I can figure out that in order to get this amount of power, we'd have 4.47 amps of current going through the circuit. And now, another version of the formula for power, P equals V times I, or V equals P divided by I can figure out that the voltage would be 0.89 volts. So that's the induced voltage in this case. Well, now, if I look at this, the induced voltage, which is an EMF, so that's right here, is equal to a magnetic field strength times length times velocity. Well, at this point, I didn't have this. So now I've got to go back up here, and I did get the current, and I can put that in the Fabel formula, so I can use this to find the magnetic field strength. So in the length of the wire that's moving across the magnetic field is 0.10 meters, 4.47 amps, 1 newton, so I get around 2.2 Tesla. So in this case, now I can use the voltage that I just got up here, the 2.2 Tesla, the length of the wire, which I already know, to figure out the speed it was just being pulled. And so that's about 4 meters per second. So there's a lot going on here, but if you notice, I actually had to figure out the strength of the magnetic field first before I could get the speed. So, like I said, I made this question up. I think I probably did it in a little bit of a backwards order. But I'll post the PDFs for that as well, so you can look at those. So this was actually problem number 6 out of the chapter 25. It says you've got a river that's 23 meters deep, flows at 4 meters per second to the east, and the Earth's magnetic field strength is pointing north at this point of the globe, and it has a strength of 50 microtesla, which is 5 times 10 to the negative 5th Tesla. And it's directed north. So it said use the bottom of the river as a reference frame of 0 volts. And what's the potential for the voltage at the surface of the river? So this is kind of like one of those problems. I think I called it, there's a rule for this, and I forgot it, because I'm doing this right now. But there's a rule for this, and I gave the example of me flying around like an airplane with metal wings. The Hall effect, that's it. So this is like a Hall effect problem. I don't even know if your book uses that term. But essentially what I can say is if the magnetic field is pointing north, the river flows to the east, I can use my right-hand rule, my flat right-hand rule, and figure out that, hey, there's going to be a force directed, in this case of this picture, out of the page. In the case of the river, it would be to the top of the river on the positive charges. So therefore, you would get a positive potential at the top of the river, and you could figure out how much that would be by using this formula, B times L times V. So the length of this is really the depth of the river. The speed is the speed at which the water is flowing, which is the conductor, and the Earth's field is 5 times 10 to the negative 5th Tesla. So I get about 0.0046 volts, positive volts, at the top of the river. Hope these two help a little bit with some of the problems that you're going to have that are going to be due Friday.